Justin Miller here, Oxford College Physics, back in action. All right, so last thing that we left off with was looking at a current loop in a uniform magnetic field. So we have ourselves a nice little rectangular loop here, has dimensions A by B, and we have a current I that in this particular situation is cycling around in a clockwise manner here, and then we've got our uniform magnetic field directed into the board, B hat. And what we did is we looked at these four sections, section number 1, section number 2, section number 3, and section number 4, and ultimately found what the force on each individual section was. So we were able to discern that the force of interaction on this section would be in this direction by utilizing the right hand rule, fingers in the direction of the current, palm in the direction of the magnetic field, thumb is then in the direction of the force. So we've got this nice F hat 1 across this segment, and then we had this segment here. Current's going this way, magnetic field's into the board, force is upward. So we have this force distributed across this segment, which we could call F hat 2. This segment, current's going down, magnetic field's into the board, the force then is this way. So F hat 3. And lastly, we've got this bottom segment, segment 4. Current's now going that way. Magnetic field's into the board. Force is downward. And this was a grand. There we go. And what we ended up finding was, in fact, that the magnitude of F hat 1 was equal to the magnitude of F hat 3. The force distributed across this section is the same amount of force distributed across this section. And likewise, the magnitude of F hat 2 was equal to the magnitude of F hat 4. And, well, what did we get with that? Well, for these individuals, we ultimately had that the magnitude of the force is I times B times the length of the section, in this case, IBB, and magnitude of the force on segment 2 and segment 4 was I times B times A. So this is what we had in terms of the magnitudes, and by direct inspection, we have that F hat 1 is oppositely directed with respect to F hat 3, thus they cancel each other out. F hat 2 is oppositely directed in terms of F hat 4, those two would cancel each other out, and overall, the net force on the loop is equal to a 0. And we said, wow, that's amazing. The net force is 0. What's going to happen? There's some flexibility in these wires here. We'll have some sort of distortion that takes place. Maybe it could form into a circle, but ultimately, nothing really happens. So that's interesting in and of itself, but quite what we want to do. So what we're going to do now is we're going to see if we can get something to actually occur. So I'm going to take this same current loop, I'm just going to rotate it by 90 degrees, or equivalently rotate the magnetic field's direction by 90 degrees. So I'm going to redraw this out. So we have our current loop here, our current I going through here, and now I'm going to put the magnetic field pointing in this direction. So all over in space, we've got this nice uniform magnetic field. Pointing that way. And what we want to do, again, is look at these separate segments here. So, still got ourselves a number 1, number 2, number 3, and a number 4 segment-wise. And we can go ahead and start looking at the individual forces on those segments. So, we can look at the force on segment number 1. Well, again, in general, we have that it will be I times B times the length of the wire, which was B in this case. This is B by A. So IBB times the sine of theta 1, we'll call it, where theta 1 is the angle between I and B, which is 90 degrees. So we've got that theta 1 is equal to 90 degrees. Thus, the sine of 90 being equal to 1, we are left with f hat 1 being equal to I, let's do magnitude, I times B times B. That's what we had before, IBB. Let's see about the direction of this particular force now. So we've got the fingers point in the direction of the current upward, palms in the direction that the magnetic field is pointing that way, which leaves our thumb in the direction of the force. So that was into the board. So across this wire, we've got this F hat 1 directed in. We come up to segment number 2. So number 1. Number 2. Well, we've got that the magnitude of F hat 2 will be equal to I times B times A times the sine of theta 2. What is theta 2? Theta 2, again, is the angle between the direction of the current and the direction of the magnetic field. We're pointing in the same direction. So, what do we have? 0 degrees, that's right. 0 degrees, and the sine of 0 degrees is equal to, yes, 0 indeed. So we've got overall, F hat 2 is equal to 0. There is no force distributed across that top segment there. Interesting, yes. Moving onward, we got this segment number 3. The magnitude of the force distributed across segment number 3 will be equal to the current multiplied by the magnetic field multiplied by the length of that segment, which is B, times the sine of the angle between them. We'll go ahead and put that in, the sine of theta 3, and we note that theta 3 is equal to 90 degrees. Current's down, magnetic field's to the right, and that then leaves us with the magnitude of the force being equal to I times B times B. All right, there's the magnitude of the force. We also need to note its direction. So we look at the direction of the current downward, cross into the magnetic field, which is pointing that way, and left with my thumb pointing out of the board in the direction of the magnetic field force. Thus, we have ourselves F3 hat as such pointing outward, and we've got one more segment to go with. Let's do it over here. Got the magnitude of F hat 4 is going to be equal to I times B times A times the sine of theta 4, where theta 4 is equal to 180 degrees. We've got the currents going that way, and the magnetic field is that way, 180 degrees, and we know that the sine of 180 is a 0, so we've got that the force, number 4, is equal to 0. So if we ask ourselves, what is the net force on the system? Net force on the loop is, well, it's the sum of all the forces acting. F2 and F4 are both 0, so we really have an F1 hat plus an F3 hat. And what are we going to get with that? Well, they have equal magnitudes, IBB, in opposite directions. Ooh. So that force is equal to 0. Get the same result that we had regarding the prior system in terms of the net force. But that's not all we've got going on. Come over here, grab a little piece of something, and see what we have. So, is anything going to happen, is the question. And the answer is yes, definitely. the orientation of these forces is much different than when in that orientation. So what's going to happen here? We'll consider this outer portion to be the current loop. And think about, well, what happens if you take something like this, and one side you have a force that way, inward, and the other side you have a force outward. Oh, it wants to rotate. We start getting a torque. These forces substantiate a torque acting on this current loop. And we know what torques do. They produce a rotation. So that's what we've got. This side has a force outward on it. This side has a force inward on it. Those are radial forces in this orientation. Excuse me. Those are tangential forces in this orientation. And we've got that it'll rotate. It rotates into this orientation. And then what? We have the magnetic field is pointing just like that. And then we have that the net force is equal to 0. And those forces are all radial forces. No tangential components. So at very least, what we're getting out of this is this object wants to rotate through the quarter rotation and then kind of lock up into this position. So there's some mechanisms that we'll come up with in order to produce a sustained rotation. But the main thing here is we get a torque. So let us go ahead and look at that torque, quantify it out, and then proceed onward. So, let us go ahead and make this a little simple on us, and we will make a fixed axis of rotation. So I'm going to take this system here, just going to get rid of that. I'm just going to put like an axle down the middle. So that we have a fixed axis of a rotation. So with that axis of rotation, we've got some radial distances away from the axis of rotation at which these forces are being applied. We have that this distance will be an A over 2, and this distance will also be an A over 2. And what do we remember about torque? Well, hopefully we remember the torque. Tau hat is equal to R hat cross F hat. Cross product picks out the mutually perpendicular components between the two vectors. R hat is a vector that points from the axis of rotation to the point of the application of the force, and F is that force. So if we just look at tau magnitude, we have that can be written as RF times the sine of theta. Again, where theta is the angle between R hat and F hat. There's the torque. Well, R is just the magnitude of the vector R hat. If we wanted to draw those vectors in, we would have this side. We've got an R1 hat for this side. We've got an R3 hat. There's their directions pointing from the axis of rotation to the points in which the forces along segment number 1 and segment number 3 act. And then, well, we've got the forces themselves. So, let us not just consider the magnitude, however. That's great. We can get the magnitudes. Also want to get the directions. So first off, the magnitude of tau 1 is going to be equal to, well, R is going to be A over 2. F is going to be equal to IB times B. And then we've got the sine of theta. So we got A over 2 times I times B times B times the sine of a theta. I want to be careful calling it theta 1 again. Let me just call this theta sub tau. So we're talking about torque. So there we go. And then we've got ourselves the magnitude of the torque on the right side is going to be A over 2, the radial distance away from the axis of rotation, at which the force, I times B, here's F3 right there, times the sine of theta tau 3. So there's the torques in terms of their magnitudes. What about the direction associated with the rotation itself? Well, let's take a look at that. We've got ourselves a cross-product relationship, and with cross products, we can use the right-hand rule. Fingers the first vector, palm the second vector, thumb is the resultant vector. So let us look at the direction of the torque that is exerted on this side right here. So we've got ourselves the radial vector points in that direction. Then we've got ourselves that the force vector points into the board, which leaves us with the torque vector being downward. So on this side, we've got ourselves tau 1 hat is down. We'll get to that momentarily. Let's go ahead and look on this side here. Well, this side we've got the radial vector is pointing this way from the axis of rotation to the point of applications of the force, and the force is out of the board, which leads my thumb downward in the direction of the torque. So on this side, we've got tau hat 3 like that. We've got their magnitudes are equal. We have to discuss this a little bit. The magnitudes are equal, and we've got that they're in the same direction. So torque vectors are a little strange to look at in terms of the directionality. They're perpendicular to both the radial direction and the tangential direction, which is awkward at best. But what we've done in the past was talk not about the direction of the torque so much, but the tendency of the direction of the rotation that that torque would produce. So this side wants to go in, this side wants to come out. They both want to produce the same directionality in terms of the rotation, which, if you're looking down on this, would look like a clockwise rotation. You happen to be above it, watching it downward. But nonetheless, the main thing here is they're in the same direction. And in this particular orientation, the force inward in the radial direction that way, there's a 90-degree angle in between that force vector and the radial vector. And really that's on both sides, 90 degrees, 90 degrees. But as the object begins to rotate, that particular angle, which we're calling here theta sub tau 1 and theta sub tau 3, that angle changes. Eventually, when it's back into the original orientation that we had, with the magnetic field penetrating through the entire loop, we have that those force vectors are completely radial, and well, theta is equal to 0. So under that quarter of rotation, it goes from 90 degrees to 0 degrees. And the torque goes from its maximal amount and reduces down to 0. So we got this. The net torque, in terms of its magnitude, is going to be equal to the sum of these two magnitudes. And we can just look at magnitudes because they both produce torques in the same direction. And these two angles, theta tau 1 and theta tau 3, end up being the same angle, as long as this is a rigid object in one plane, which is all that we're dealing with here. So we've got 2 times either one of these gives us the overall torque. 2 times is just going to take away this 2, and we can write this as IBAD times the sine of theta, and we'll call it theta sub tau. There is the net torque on the curved loop. Fantastic. As it rotates, theta sub tau goes from 90 degrees to 0 degrees, and at 0 degrees, net torque is equal to 0 itself. And that's when we're back into this situation. The magnetic field now, in terms of the alignment, this way, and we've got torques that are equal to a 0 because of the orientation of the forces with respect to the loop itself. So it rotates from this orientation into this orientation with respect to the magnetic field's direction. So let's get it like this here. So some other things that we can do with this is what happens if we have kind of a winding of wires here. So it's not just one singular loop, there's n loops of wire. Well, each current ultimately interacts with the magnetic field and exerts a force. So really by having multiple windings of this for a given current, it's like amplifying the overall current in any given location, which amplifies the force, which then amplifies the torque itself. So we have a wire, or a loop, I'll say, with n turns. For a loop with n turns, we can write the magnitude of the net torque is equal to NIB times the sine of theta sub tau. And it's just the number of loops. Every successive loop gives an amplification of the overall torque. However, in general, every additional loop also adds in more mass to the system, which changes the moment of inertia of the system, which then has an effect on what sort of angular acceleration is produced. So it comes at a price. We're not going to be really worried explicitly about the angular acceleration, such things. That was kind of last semester stuff, but that's stuff that we can start thinking about, right? That torque produces the angular acceleration, about the moment of inertia, and go from there. One other thing that can be done, not going to show it here, it gets a little bit messy, but it can be shown that area enclosed by the loop A can replace our A times B. And that's in general. So this can be solved out ultimately for any shaped loop, circular loop, triangle loop, whatever you want to do. And it turns out that it's only the area that the loop encloses that ends up being fundamentally important. The dimensions themselves correlate with the area enclosed, but really it comes down to this. The net torque can be written as NIBA times the sine of theta sub tau. A is the area, B is the magnetic field strength, I is the current, N is the number of loops, and theta is the angular orientation of the loop with respect to, the angular association of the radial vectors with respect to the force vector. That's it.